Okay, let's get started. Lecture 14. Just a heads up, I'm still working on grading the exam. I've graded about half of it, and by half of it, I think I mentioned this last time, but when I grade, I don't grade on a student-by-student basis. I grade on a problem-by-problem basis. So I grade like problem 1 for everybody, or problem 2 for everybody, so that I make the same deductions. So far for those two problems, the average is like in the 80s. So I mean, the class is doing fine. So I'm not really concerned at all. We're up to date on homework assignment grading. 3.1 was due today. Hopefully that was an easy one. I'm hoping that was pretty straightforward. And I'm also hoping that by now everybody is comfortable with the aspect of computing a cross product. Okay, that should be pretty straightforward enterprise. We're going to be doing it a lot. And sometimes in class I might skip the steps of, like, I'll set it up and then I'll just say, like, here's the answer. But we won't probably do that until later. Like, we're still sort of getting used to it, but I just want to throw that out there. I'm sure some of you might have heard this on email, but we do have a career fair on Wednesday, September 25th from 12 p.m. to 4 p.m. So it would be right after this class on Wednesday for 4 hours in the rec center. So don't forget. Okay. Any questions? And did everybody get the code? Okay. So today, if the last lecture was about, a math topic, like a cross product, today is about why did we talk about that? And so what we're going to do today is formally define one of the real concepts of application in this class, which is a moment. If you ever talk to anybody who's like been through an engineering curriculum or a practicing engineer, you ask them what is statics about, a common answer you might get is forces and moments. I mean, that's a really common answer to that question. Let's just make sure that we're all on the same page, though, with a cross product. So first off, a cross product of two vectors A and B yields another vector such that the magnitude of that vector is equal to the area of the parallelogram formed by those two vectors emanating from the same point, and then the direction of that vector is normal to that parallelogram, normal to that plane. And the way that we evaluate a cross product is through the use of a determinant. And really what the last homework is about was the two different ways that you can evaluate said determinant. You can do it using the rule of Saris, or you can do it using cofactor expansion. I mentioned this in class last time. I will probably in my examples use cofactor expansion a little bit more because I think it makes the bookkeeping a little easier when it's all said and done. But I don't care which method you use. You can use either one. It doesn't matter to me. Just as long as you get the right answer at the end. Okay. So far so good? Okay. So today what we're going to do is we're going to sort of introduce the problem today associated with where moments are necessary. And so I want to talk about rigid bodies. I want to talk about forces and moments. I want to talk about the principle of transmissibility. That's a lot of word salad. Instead, let's deal with two really basic problems. Okay? So I want to paint a couple scenarios for you, and let's discuss them. How many of you have ever played Jenga before? Okay, everybody knows what Jenga is, right? So I think that it's fair to say that Jenga is all about the concept of stability, okay? In other words, as you play the game, the tower gets more and more unstable. That's really the whole point, right? Okay, so I present to you a challenge, okay? Let's say that I had a Jenga tower right here on this table, okay? It was kind of tall, so it's starting to get a little flimsy. And then I told you that I present you a challenge. I want you to take this Jenga tower and I want you to move it from here to here, across the table. And I want you to do that using only one hand, okay? So here's the Jenga tower, and I want you to move it across the table using only one hand. I'm not saying that there's a guaranteed method of success. But for those of you that would think of attempting to do this, what way would you do it? Somebody tell me how you would do that. Here's the Jenga tower. How would you move it from here to here?
Push it along the bottom.
You would push it along the bottom, okay? So in other words, if here's the ground, okay, and here's the Jenga tower, you're telling me that this would be probably the best way of doing it, as opposed to pushing it right here. Is that a fair statement? Now, why? Why are you saying that? And it's okay if it's just like, that's what my gut tells me I should do, but do you have a reason for wanting to push it on the bottom as opposed to the top? Let me ask it this way. What do you think would happen if you pushed it on the top?
It's going to tip over.
It's going to tip over, right? There's something in your gut that says if I push it on the bottom, it has a less tendency to do that, right? Okay. All right. So let me put a different thought behind this. Would you agree that if imagine we were like in your dorm room or your apartment and we're trying to push a sofa across the living room floor. The sofa is going to push back, right? There's going to be some friction that we need to overcome between the sofa and the carpet or whatever your floor is made out of, right? Okay? I propose that pushing the Jenga tower across the table, there's going to be an opposing frictional force going the opposite direction, right? And so what I'm saying is that, okay, your gut tells you need to push it on the bottom as opposed to the top. How about this? Maybe a better way of saying it is that if you want to achieve stability, stability in this case is trying to prevent the Jenga tower from toppling over, that maybe what we ought to do is keep these forces together as close as possible. Does that make sense? That really what we want to do is keep these forces close together. Now, here's this problem. Let's talk about another one, okay? So here we have a mechanic, and this mechanic is really trying, putting some effort in to try and loosen this lug on the bottom of what looks like a piece of industrial equipment, okay? My question is, why is the mechanic gripping this end of the wrench? Why is the mechanic gripping this end?
Leverage.
Leverage. That's right, but why is leverage? Why does that matter?
Easier.
Easier to do what?
Turn the lug.
To turn the lug, okay? The key word here is rotation, okay? And in fact, rotation is the key word in both of these scenarios, okay? All right, I propose that what we have here in this scenario is we have a fixed point of interest and we have a mechanic applying some force. And that in order to generate the maximum amount of rotation, what we're trying to do is take this force and get it as far away from this point as possible. That the further away this force is from the point of interest, the more rotation we will generate. Does that make sense? Everybody okay with that? Okay. What we're talking about with these two scenarios is the difference between translation and rotation, okay? But the other thing is that we have scenarios where the forces don't meet at a common point. If we go back to the examples that we did last time and up through the first exam, all of the free body diagrams that we drew, whether we were dealing with static equilibrium, 2D, 3D, we had all the forces all meeting to a common point. But that's not what's going on right now. Now we have situations where we have a point of interest and the force is not going through that point. It's going some distance away from that point, okay? Now, what does that lead to? That leads to rotation, okay? Let me give you an example, all right? Let's take this structural system that I have right here on the slide. So I have some lever or some beam that is supported there in the middle, and I have a 20-pound force going down and a 20-pound force going up. Now, I propose from a sum of forces in the y direction and sum of forces in the x direction perspective, this system's in equilibrium, right? Because I have 20 pounds going down and I have 20 pounds going up, right? So the sum of forces in the y direction is 0, and there's nothing going on in the x direction. But let's just have some common sense. Is this system in equilibrium? No. I mean, imagine if you were on the playground, you were looking at the seesaw, and you were sitting on one end of the seesaw, at the same end your friend on the other end was lifting it up. You would, boo, you would fall over like crazy, right? That wouldn't work, right? I propose that what's going on with this system is that it is achieving equilibrium from a translation standpoint, but not from a rotation one, okay? So now I'm going to introduce to you some new definitions. Now, we have been dealing with forces this whole semester. Now, if I were to ask you to define a force, you'd probably say force equals mass times acceleration, or you'd say it's measured in pounds or measured in newtons. But let me give you a different way of thinking about it. I propose that forces are actions on bodies that increases that body's tendency to translate, okay? But if a force increases its tendency to translate, we recognize up here that that's not enough to guarantee equilibrium. So we need a new term. We need a new term that talks about an action on a body that increases its tendency to rotate. Okay? We have a name for that. We call it a moment. Okay? Some of you are probably going to think of an analogous term with moments. You're going to think of torques. We typically refer to them as moments in an engineering mechanics perspective, but torques and moments have a lot of similarities in their definitions. But what is a moment? A moment, at least from a textual vernacular description, would be an action on a body that increases its tendency to rotate. But how do we compute a moment? Well, we're going to talk about that here in a second. In fact, let's do that now. So I propose that the formal definition of a moment is going to be defined as R cross F. Okay? So I've got this 3D image here, but just to sort of illustrate that, and I'm not drawing this on the screen because I'm going to simplify this and generalize this here in a bit. If I have a point here of interest, we'll call this, I don't know, point A. Here in the slide, I call it point O. Doesn't really matter. And I have a force, some force here, okay? That force is defined by some vector. What I will then do is define another vector right here. We'll call that vector R, that goes from our point of interest to where the force is being applied. And then I propose that the moment is defined as R cross F. And that is going to be our formal definition of a moment. We're going to get into here in a second why we define it that way, why it's R cross F and not F cross R. There is a very specific reason for that. But that's going to be our formal definition. Okay? Another thing that's worth mentioning is, what about the magnitude of that moment? Okay? Well, if I go back to this system right here, here's point A, here's our force vector. If I want to determine what is the magnitude of that moment, like what is the magnitude, bless you, of that, which we could just call MA, I propose that it equals the magnitude of the force times this distance d. And I'm going to call it, there's a name for d, I'm going to call it a moment arm. What is d? D is the distance, the shortest distance, I should say, the shortest distance between point A and this force. So think of that as this perpendicular distance here. We'll call that d. Okay? So if you want to define the magnitude of a moment, like conceptually, that would be our magnitude. The magnitude of this force times the shortest distance here. And since we're dealing in scalars, It doesn't matter if it's DF or FD, because scalar multiplication is indeed commutative. That's really all that this slide is saying. Okay? All right. With me so far? Now, this term, now bless you. One thing that I have defined, what I'm going to say is very specifically, is this term R. I'm going to generalize R here in a little bit, but everybody with me so far? Okay. Now, what we need to do now in order to generalize our definitions here is I'm going to take a step back and I'm going to talk about the principle of transmissibility. Now, that's a really mouthful word here, but in order to describe the principle of transmissibility, I want to talk about the tug of war. We've used the tug of war analogy a while back, but let's go back to this in our head. So we have this blue team and this purple team that are playing a game of tug of war. Okay? Now, in the game, I've got these blue force vectors that are being applied this way, and I've got these purple force vectors that are being applied this way. Okay? Now, let me ask you a question. Would it, at least from a vector perspective, would it really matter if these two guys switched orders? Like if this guy was up here and this guy was back here, would it really matter? Why? Why doesn't it matter? It's all on the same line of action, right? They're still doing the same thing, right? Whether person number 3 is here or person number 3 is here, they're still pulling the same force along the road, right? Does that make sense? Okay. The principle of transmissibility states the following. If I have some line of action out in space, okay, and I have a force vector on that line of action, I could take that force vector and move it anywhere along that line of action, and it would retain the same static equilibrium. In other words, if these two lines of action were laid on top of one another, and I have one force vector here and one force vector here, and these were the same vectors, if these two lines of action were laid on top of one another, they would achieve the same equilibrium, or they would have the same static contribution in terms of both forces and moments. Okay? Is everybody with me on that? Okay. So if that's the case, I want to look at my better definition of R. And I should have, I think this little box here was supposed to show up later, but alas. Now, the magnitude of the cross product is formed by the area of the parallelogram that forms two vectors. Okay? So I've got here my nice little animation here. Okay? I want to take a look at this. Okay? This is a neat little fact of geometry, that here I have this green parallelogram that I propose the area of that parallelogram is defined as the base times the height. And the height is this perpendicular distance, sort of akin to that moment arm I drew over here, right? Now, notice how the green parallelogram is changing throughout the animation, right? But one thing that's not changing is its area, okay? You'll find that, yeah, we're getting different parallelograms, but these parallelograms all have the same area, every one of them, okay? So from this analogy, what I'm going to do is this. I'm going to more explicitly define things. So what I've got here is F is going to be the force vector, and in the case of this, F is along this line of action.
Thank you.
F is going to be along this line of action, and F is going to retain a consistent magnitude. The magnitude is going to be whatever the base of this parallelogram is. So with this analogy, I'm going to define a better I'm going to come up with a better definition for R. I'm going to call R a position vector. Okay? R, this is going to be how I define R. This is what R is going to mean. R is going to start at the point about which we're taking moments. Okay? it is going to end at any point along the line of action of F. Okay? So I really, this is sort of a wild idea, but I promise this works. I'm actually going to demonstrate to you here in a second that this indeed does work. Okay? So let's say that I have a point here in space. Let's call this A. Okay? And let's say that I have a force going along this line of action. So here's my force, okay? And I want to determine the moment generated by that force about this point, okay? Now, what is R? R starts at the point about which moments are taken, so it starts here, and I propose that it points to this line of action. So a valid definition for R could be this. We'll call that R1. But another definition for R could be this. We'll call that R2. And some of you are going, wait a minute, Dr. Mike, I don't understand. So you can have R1 cross F and R2 cross F. Aren't those going to give you different answers? No, they're not. I propose to you that if we evaluate both of these cross products, we're going to get the same answer. We're going to get the same answer because whether your R vector points like this or it points like that, you get the same magnitude of the moment. And I'm going to show you how this works here in a bit. This is also why moments are defined as R cross F, not F cross R. Okay? This is why they're defined that way. But I promise you that this is true. Okay? And I'm going to show you that this works with this example. Okay? So let's look at this example. Okay? So this is a very 3D example, so we're going to take our time with this. But I have a rectangular plate, and it's supported by a wire between these points C and D. Okay, so there's a wire between C and D that's holding this thing up. And the tension in that wire is 200 newtons. What I want to know is how much moment does that force generate at point A? And we're going to do it two different ways, okay? So one way we're going to do it is we're going to use, so point A is our point of interest, okay? We're going to use one R vector that goes from A to C. Then we're going to use another R vector that goes from A to D. And I propose if we do R cross F using this vector or R cross F using this vector, we will get the same answer, okay? And if you don't believe me, we'll see. Okay. Is everybody with me so far? Now, we're getting into a lot of 3D land, okay? We're getting into a lot of 3D land. So I'm going to propose maybe a slightly different way of handling 3D. Let's start doing point coordinates, and keep in mind that these point coordinates are going to be in millimeters, okay? By the way, we're going to be doing a lot of vector writing, and I'm probably going to start getting into the habit of now writing the units outside the vector and just putting numbers inside the vector. I wasn't doing that with forces, but now with forces and distances and moments, it's going to be a lot of unit writing, so I'm just going to put the units on the outside. All right? So what I'm going to do is I'm going to write down some coordinates. I'm going to write down coordinates for A, B, C, and D. So let's see if we can just define what are the coordinates of these points. So keep in mind the origin is right here. So if the origin is right here, okay, keep in mind that this is, it's sort of cut off here in this upper image. But this is the x-axis. This is the z-axis. This right here, that's the y-axis. Sort of goes like that. Okay, so x, y, and z. Okay, so let's start off with point A. Can somebody tell me what are the coordinates of point A? I mean, point A lies along the z-axis. So what are the coordinates of point A? So I'll help you out with A. So it's going to be 0, 0, then it's going to be 320. Does everybody see that? This is point A. So this is the origin, right? So we don't go over X, don't go up Y, but we go along the Z-axis. For A, we go 80, then 240, so we go 320. Does everybody see that? Let's just point coordinates. Let's just do that, okay? So if that's the case, what are the coordinates of B? 0, 0, 80. Okay. Okay. All right. What about point C? What are the coordinates of point C going to be?
Is it 300, 0, 400?
Exactly right. Okay, what about D? Do we have any X value? No. What about Y?
240,
And then Z?
8.
There you go. Okay. Does that make sense? All right, so far so good? Okay. All right, so in order to do some cross products, we're going to essentially need 3 vectors. We're going to need a force vector, but we're also going to need these 2 position vectors. Let's do the position vectors first. Okay? So we're going to have one position vector that goes from A to C. Because remember, A is our point of interest, and it's got to start at our point of interest and go to the line of action. So we'll do this one, then we're going to do another one that goes from A to D. Okay? Does that make sense? So, so we're going to have position vectors, okay? And so the 2 position vectors that we're going to have are going to be vector AC and vector AD. Is everybody okay with that? Okay. Now I'm going to introduce some new notation, and I'm introducing this because this is what the textbook uses. There's actually some logic though behind it. It's actually pretty nice. Instead of vector AC, what I'm going to write it as this. I'm going to write it as this, which basically means the vector 2C from A. Okay? The reason why this is kind of nice is because what I can do is I can say, well, point C is that, point A is that, and if I subtract the 2, what do I get? I get 300 minus 0, which is 300. I get 0 minus 0, which is 0, and this is 80. So therefore, that position vector is that. And by the way, that's in millimeters. So I'll stick that there on the outside. Does that make sense? And if you don't believe me, look at, let's just go at the very top, right? So how would you get, I mean, think about it. How would you get from A to C? Go 300 in the X, nothing in the Y, 80 in the Z. Does that make sense? So it's another way of doing it. And I'm doing it this way because I want to connect it to this new, C/A notation. So this is R, whoop, wrong color. So this is D/A. And so I'll take point D. Point A. Subtract them. And 80 minus 320 is going to be what? Negative 240? Is that right? Bless you. Okay. So what do we have? We have R then we have R and then from a units perspective, these are both in millimeters, okay? So this is 300 millimeters plus 0 millimeters, 80 millimeters. Instead of writing the units on every term, I'll just stick it over here on the outside. Does that make sense? So the idea behind these over here is that I'm going to take one of them cross with our force vector and take the other one cross with our force vector, and I'll get the same answer, okay? So speaking of, let's do that force vector. Okay, bless you. Okay, so what is the line of action for that force vector? It's CD, right? Everybody see that? CD. So how do I go about that? Okay, so let's do that. By the way, what is the magnitude of the force?
200 newtons.
Okay. So from C to D. Is it okay if I scroll this up a little bit? So I have a little bit of room? Okay. So how are we going to go about this? Well, we need CD. So we'll take point D and point C. Point D is 0, 240, and 80. Point C is 300, 0, 400. We'll subtract them, okay? And what do we get when we do this? We get negative 300, 240, what, negative 320? Fair statement? So therefore, CD is negative 300I plus 240J minus 320K. What are the units for CD, by the way? Millimeters. Because that's just a distance vector. Okay? This is a distance vector. This is not a force vector. How do I turn this into a force vector? What do I do?
Multiply it by the magnitude.
multiply what by the magnitude? I mean, remind me, hold on. What's our formula? We would say that a force vector is a force times what? The lambda. What is lambda?
Direction.
A direction vector. How do we turn this into a vector that contains only direction? Divide it by its own magnitude. Remember that? So what we need now is we need the magnitude of CD. So okay, and when we check that out, what do we get?
500.
500 and 500 what?
Millimeters.
Millimeters. Because that's the length of the vector, right? Remember, this vector's in millimeters, so this is millimeters, this is millimeters, this is millimeters. Maybe if I need to, on this calculation, we can say millimeters, millimeters, millimeters. Okay? Now, so I mean, tell me what to do. How do I turn this into a force vector? Tell me what to do next. Take this, divide by its magnitude. So therefore, okay, and so if I just write this out in decimal form, here I'll put this down here so I don't squunch it up. What is that? Negative 300 over 500, what's that? Negative 0.6. 240 over 500, what's that? 0.48. Did I get that right? Oh, 0.6i. And what's that one? 64? 0.64? Is everybody with me on this? Because we've done this before. I mean, I just want to make sure this part is comfortable. What are the units for this?
Units.
There are no units, right? So I'm going to go ahead and put that there to make sure we're all on the same page. So now, if I want my force vector, I take my magnitude of 200 newtons, multiply it by this. So So what do I get? I get 200 times that, which is negative 120. That's going to be 96. And that's going to be 128. Now what are the units of that vector? Newtons. Okay. Okay. Now I want to take a step back because as we were doing this calculation, I kind of had a feeling I was blowing some folks' minds here. So let's take a step back. Does everybody see what I'm doing here? I'm taking a distance vector. A distance vector is not a force vector, but it does tell me the direction. It tells me the direction of that force. So if I divide the distance vector by its own magnitude, what I get is a vector with a length of 1. I mean, if I do square root of this squared plus that squared, I get 1, right? So if I take this vector, multiply it by 200 newtons, now I get a vector that has a length of 200 newtons in the direction of that force. Everybody okay with that? All right. So now I've got these three vectors, okay? And I propose to you that r cross f equals r cross f. That if I do the cross product of these two and these two, I'll get the same answer, okay? Let's see if I'm right. Okay. Has everybody got all this? All right. Okay. So let's do the first one. Okay? Okay? So how are we going to do this? We're going to set this up in a matrix, right? The top row is going to be ijk. The middle row is going to be these terms. Bottom row is going to be these. Okay? Now, like I said, I'm going to use cofactor expansion. I kind of like that one better than the rule of Saris. That's just me. So, remember, strike out the rows and columns, and I get strike out the rows and columns. Strike out the rows and columns. Okay. Okay. Is that okay? Everybody with me on that? All right. So let's do the first one. All right. So what do we do? How do we do this? We go this times this minus this times this. So what's 80 times 96? So this is going to be negative 7680i. Okay. Minus. Okay. This one's going to take a little bit of work, so I'll help you with this one. So that times that's going to be negative 38400 plus 9600 because it's minus that product, but it's negative. And then this one, we're going to have that times that minus 0, which ends up being 28880. Okay, so what do we get? We get negative 7680i. Let's see, what do we get here? So this is going to be a negative term inside here, but then there's a negative, so it's positive. So it's basically just the difference of those two numbers, which ends up being 28880. We'll put a comma there, there. Did I get that right? How am I doing?
I'm getting 28,800.
Oh, is it for which one? This one?
In
Oh,
total.
wait. I got that for both of them, yeah.
The 800?
I looked at that.
You're right, it is 800. Whoops. Whoopsie daisy. You're right, it is 800. Sorry. I just wrote one too many 8s. All right. Is everybody okay with that? So what happens now if I do the next one? What happens if I do r cross f but use the other vector? So 0. And then 0, that's 120. Okay. So here, let's see, what do we got? Oh, whoops. I have a typo here. This is negative, that's negative. That would help. Okay. So we're going to have that times that, which is negative, minus this times this, which is positive. So I ended up getting, let's see, 30,000 or negative 30,720 plus 23,040, right? Then over here, that times that minus this. That product's positive, so minus that. So negative that plus k. And then, what do we have? This times this minus that product's negative, so it's going to be positive. So 28,800. And so what do we get? We get negative 7. Well, by golly gosh gee, look at that. We get literally the same answer. Because again, if I have a point and I have a force along a given line of action, my position vector goes from that point to the line of action. Doesn't matter which vector that I use, I will get the same cross product every time. As long as you do the math right. So, what is the answer to the question? The answer to the question says, what is the moment? The moment is this vector. Now, for those of you with a physics background, I will tell you that it is customary when expressing units of moment to leave it in product form. Okay, in other words, Newton meters, some of you are like, well, isn't that a joule? We don't do that because joules are sort of more related to energy. And that's not really what we're doing here. We're dealing with moments and torques. And so it is customary, even in US or SI units, to leave it that way. Like foot-pounds. You know, that's sort of, you know, you can see where that connotation comes from. Okay, So that's our answer. Okay, I will tell you, and then I'll let you go, that moments will get easier as we go. We sort of do the hard one first, then we sort of take it easier. Everybody good? Homework on this due Monday. Everybody have a wonderful weekend.